Thanks. So yeah, I'll be talking about the Zephyr project. It's something I've been involved with now for about 3 years or so. Before that, most of my career I've been doing just Linux-based things, and now maybe 80% of my time nowadays goes to Zephyr. So what is it? It's a collaborative project under the Linux Foundation that was announced, I think a little bit under 2 years ago. And it's essentially a small, scalable, real-time operating system for really resource-constrained devices with very little bit of memory and processing power. And it supports multiple architectures. It can run on devices as small as 8 kilobytes of RAM. I think at the moment, if you strip out most of the things except for the core kernel, it will take some 6-7 kilobytes of memory. But then you can also scale it up. I mean, there are all sorts of features that you can enable there, connectivity and networking features to make it really capable setup. It supports multiple different architectures, like the big ones like x86 and ARM, also ARC, NIOS 2 and RISC-V. And it's licensed under the Apache 2 license, which is a permissive license. And development happens pretty much like any open source project out in the open. Mailing lists, we have the source code on GitHub and so on. And the general kind of goal of the project is to be, well, I say here the Linux of microcontrollers. What that basically means is that when the hardware scales down to levels where you cannot run Linux anymore, so we're talking about under 1 megabyte of RAM, we want Zephyr to be the choice of an operating system when somebody's looking for an open source operating system to run on that kind of hardware. It was launched in the beginning of 2016. We had 3 launching members then. That was Intel, NXP, and Synopsys. And since then, there have been several new companies that have joined the project. Biggest one, I'd say, is Linaro, that has brought along a lot of the ARM vendors to the project. We also have gotten several silver members to the project, like Nordic Semiconductor, who have contributed a huge portion of the Bluetooth support in Zephyr. There's Runtime.io also, who are actually hosting or interested in 2 different real-time operating systems. They have their own minute one. And Oticon is a very recent, I think just a few months old member that's interested in doing hearing aids based on Zephyr. The architectures that the project launched with initially included just x86, ARM, and ARC. But ever since the project was launched, we've gotten several new ones. I mentioned some of these earlier, like RISC-V. NIOS 2 is an FPGA-based platform from Altera. That's actually, I think, a subsidiary of Intel these days. And then there's the Extensa platform from Tensilica also that's supported. When the project was launched, I think we had one kind of officially supported board per architecture for ARM, ARC, and x86, but it has really massively grown since then, the kind of hardware that you can run Zephyr on. This is not the current set. I think this is a small fraction of it, what Zephyr supports these days. It just fits nicely to this matrix here. People keep on coming to us, both hobbyists and companies, all the time with new boards that they're interested in. For example, there are many ST microelectronics boards that have been recently contributed, even though ST isn't a formal, official member of the project yet. A little bit about the architecture of what kind of stuff you can find in Zephyr. We have, as I mentioned, very high configurability. You can fine-tune all sorts of features and parameters in the system depending on what kind of requirements your hardware platform has. You could basically categorize the context that code runs into three categories. You have the interrupt context, and then we have threads, which can either be preemptive or cooperative. That's essentially decided based on the priority that you assign a thread. I don't remember which way around it is, but negative priorities are one type and positive priorities are the other type. For the most part, all of the memory resources are statically allocated, so you get a good idea upfront what's the upper bound of what the OS will be consuming memory, which is important if you have a really small amount of it available anyway. There are some high-level objects that can be used to get kind of dynamic memory allocation as well. There are memory pools and I think they're called memory blocks or something like that. We have a wrapper for the commonly in other OSs found malloc and free APIs, which then underneath use, I think, the memory pool API. But for the most part, the code in Zephyr is just using static arrays to allocate things and use those. Unlike most other open source real-time operating systems, we have a huge amount of kind of high-level functionality, while others mainly have just the core RTOS. We have a very rich networking stack and Bluetooth stack in Zephyr, supporting the very latest Bluetooth 5 specification, as well the Bluetooth mesh specification that came out just a few months ago this year. And there are features like power management, and we have our own crypto library also that's part of the Zephyr tree. A little bit on how we see the project and how you could kind of split it into certain parts. So at the very core, we have the OS itself, which you could group into three main layers. At the bottom, you have the kernel and the hardware abstraction layer. And that's kind of, when I talked about earlier, getting the smallest possible footprint out of it. In that kind of configuration, that's most of what you have will be the kernel and the hull, and then we'll have a tiny amount of stuff on top of that. But then, if you have more memory available, you can enable more of the things from the higher layers. So we have in the OS services, you'll find things like the networking stack, the IP stack, the Bluetooth stack, the crypto library, and such things. And then at the highest layer, we have kind of high-level networking protocols, mostly IP-based protocols that you can do, and high-level or higher-level objects that you can take advantage of. And then if you step outside of the Zephyr OS itself, we have the Zephyr Project. So this would then be the software development kit that we ship as part of it. Their device management, bootloader. The bootloader is actually managed as a separate project from Zephyr. The one that we intend people to use is called MCU boot, which will be then responsible for updating the OS images and so on. And then there are things which are not formally part of the Zephyr project. People that have done clones of the project or done various kinds of extensions to it. Some examples could be, for example, MicroPython that's been ported. We have a JavaScript implementation also that you can write JavaScript code and run it with the help of Zephyr. And most of these kind of Zephyr community projects or features we necessarily don't even know about because they're not a formal part of it, and it's free for anybody to use. So the ones I've listed are kind of the main ones that we know of in the community. A little bit about how it is to develop with Zephyr. We are using GitHub to manage the code. Also, the issue tracker is GitHub based. And you use typical GitHub pull requests to get your submissions to Zephyr. You can build the code on both the Linux, Mac, and Windows. Linux has a few things which others don't have, like integration with the QEMU emulator, which I'll, if I have time, I will show you a little bit later how that works. There's lots of sample applications in the tree if you find the documentation of the APIs insufficient, so you can just look at how things are done. And many of those are good starting points also for doing your own applications. And integration with the hardware that Zephyr supports is built in to the build system. So most of the time, most boards, to get your image onto them, is just a matter of running make flash. I think there's a make debug target as well, which will then give you a debugger to see what's happening and so on. Even though we support all three of these platforms for developing the code, it's actually quite easy for somebody with a Linux background like myself to get into the project. Especially somebody who's been doing Linux kernel development. So the Zephyr project uses the same kconfig language to describe the features that you want to build into the kernel. So you have the same kind of user interface, a menu-based system that you use to configure and select exactly what you want to have in your image. It's also using the kbuild to actually build it, but that one will be phased out, I think, still during this year. I think it will be making the next Zephyr release. We're switching over to CMake in order to cater for some IDEs, especially on Windows. You get better integration there with those. We're also using device tree definitions from Linux to describe the boards that we have and what kind of peripherals they have, what the memory addresses are, interrupts, and so on. And on Linux, if you don't have hardware to run on, or if you just want to experiment without the hardware, you can use QEMU to run your code. A little bit about what the key focus areas of the project are, what we see the project going to in the future. Perhaps one thing which I see constantly repeated and talked about in the project is security certification. So getting Zephyr to security sensitive use cases. So there are certain features that are being developed right now to enable this. One is, for example, the ability to have a split kind of kernel, and I guess you could call it user space, where you can have different privilege levels of code while it's running and what memory it can access and so on, which would then make it possible to certify, for example, the kernel part, whereas having an unprivileged higher layers of the stack. We are working on improving support for all three platforms, Linux, Mac, and Windows. The Mac and Windows support hasn't been quite on the same level as the Linux, but that's gradually being fixed, particularly thanks to this migration to CMake, which will make the IDE integration more seamless. And we're trying to extend to support more compilers as well. The most common compiler currently used with Zephyr is GCC. There are a couple of the new architectures which require their own compilers, but pretty much GCC is the one that we use. But there's work in progress to bring LLVM support, for example. I've recently seen a lot of patches going into the tree to fix compilation errors or warnings that you would get with LLVM. So to a large part, we are already compatible with that. And of course, commercial compilers also. For example, Intel has, I think it's called ICC, that's optimized for Intel architectures. Another thing that we are not quite there yet is the device firmware upgrade. So there are companies that have done their own custom solutions for this, but we want to have one provided as part of the project that works pretty much out of the box for whoever wants to use it. And for that one, as I mentioned earlier, we have this project called MCU Boot. And the way that we will be doing the device firmware upgrades is we will have 2 main slots for 2 images of the OS. So you have the current one and the new one. And the bootloader can then decide which one it will boot. In addition to this, you would typically have also allocated area of the persistent memory for the file system if you need that. A bit more on the roadmap. So the cadence of the project is that we're releasing every 3 months or so a new release. We made the Zephyr 1.9 release just a month ago, actually 2 months ago already or so, and are now starting to prepare for the Zephyr 1.10 release. I think the merge window for that one is going to close in about a week or so. And a lot of the features listed here is what I mentioned earlier. We have the, actually, can you see this? Yeah, the firmware updates there. At the moment, it looks like it's going to be landing in the tree somewhere in December, which means it will probably miss the 1.10 release and be pushed to the 1.11. The project has also decided that it wants to do so-called long-term support releases. But so far we haven't done that because we have kind of a critical set of features that we want to be supported by the project before we do a long-term support release. Things that we think are really essential to make good IoT products. For example, the firmware upgradability is something that we absolutely want there because that's an essential way to mitigate if you have security vulnerabilities or something like that showing up. You need to be able to upgrade the firmware of devices which are already deployed in the field. So I myself mostly focusing on the networking and the connectivity side of Zephyr, in particular the Bluetooth side. So I'll go a little bit more into details of what Zephyr has to offer when it comes to this. First about the networking. So when the project started, we didn't immediately want to go for the option of invent our own IP stack. So we took the IP stack from another RTOS called Contiki. But what eventually happened is that we were trying to make this fit with the rest of Zephyr, and gradually it kind of diverged apart so much that it became impossible to port fixes over one way or another, and the different kind of adaptation that we had to have there made the memory footprint so large that we couldn't fit it anymore into the smallest boards that we wanted to run Zephyr on. So since a few releases ago, Zephyr has had its own native IP stack that's completely optimized for the OS using the native low-level APIs that you can find there, and has a small memory footprint as you pretty much can get with an IP stack. It supports both IPv4 and IPv6, UDP and TCP. Many high-level protocols as well. You can run it over 802.15.4 radios. We have integration with the Bluetooth stack, so you can do 6LoWPAN over Bluetooth. With that, we also have a few Ethernet drivers there, and the list is gradually growing. We have some kind of virtual drivers for QEMU usage also, so that you can combine together 2 QEMU instances and have them talk IP-based protocols with each other. And about the Bluetooth, I should mention about the networking. We're going to have another a bit shorter talk tomorrow afternoon, I think, that will be focusing on the Zephyr networking. So if you're interested in more of the details, come listen to that talk tomorrow. So about the Bluetooth support in Zephyr. We have the full stack, and this is, when I say full stack, I mean more than what you find on a typical phone OS or your PC. We have what usually sits in a dedicated chip on a PC or on a phone, which is called the Bluetooth controller. So that's the one that's talking directly to the raw radio hardware. So we have the protocol layers there, and then we have the Bluetooth host side, which then has the protocols that you would more traditionally find in in Linux, for example. Bluetooth mesh support is fairly huge new feature for Bluetooth, which we announced for Zephyr at the very same time that the specification went public. I think it was in July this year. The target boards, I think that the smallest target board that we want to run and can run Zephyr Bluetooth on has 16 kilobytes of RAM. So most of the use cases that you want to do Bluetooth with can run in that small memory. It does cause some challenges, however. So if you want to do lots of debugging, enable debugging features and so on, it's easier if you have like 32K or so more memory. If you don't have native Bluetooth radio, so you don't run the controller parts, you can also run HCI connected to another controller like you would have on a PC or on a phone, and we have drivers for that. So you can use UART or USB or SPI-based controllers. We have experimental Bluetooth Classic support as well, but that's the general target device of Zephyr is a low power one, like sensors and so on. Bluetooth Classic isn't really a good fit for these kind of devices because of the higher power consumption. So we've mainly been focusing on Bluetooth Low Energy when it comes to the stack. Then we have the IP support profile or 6LoWPAN module in the Bluetooth stack, which integrates seamlessly with IP stack that we have in Zephyr. So you can do IPv6 over Bluetooth this way. And some features which we are planning. Since we have our own controller, we can do more optimizations than what you could do if you have standard-based controller. So there are some things which you cannot do using the standard HCI interface to controllers, and we are doing our own extensions for our controller to be able to do that. For example, there are some features of mesh, some really tight timing constraints that you have with mesh which you cannot do using standard HCI. So we'll be having this, I think, in the next or the release after that one. And one Bluetooth 5 feature which we don't yet have is advertising extensions. It basically increases the amount of data that you can have in the broadcast packets going over the Bluetooth LE advertising bearer. Yeah, so if you're interested in more about Zephyr, there are actually 3 more talks here at the conference. They are shorter ones, I think like 20-25 minutes or so. There will be a talk about the mesh support in Bluetooth mesh support in Zephyr, more deeper networking overview, and then also details about the Bluetooth controller support in Zephyr, which is really a new thing in the industry when you think about open source Bluetooth solutions. So since I have time now, I thought I would kind of show you in practice, give a little bit glimpse into what it looks like to develop with Zephyr, if this works. So this will be a live demo. Let's see. Where's my mouse? There. All right. So what I have here is basically in this terminal window. Let's going to make it a little bit smaller. I'm going to be running a Zephyr application. So the idea here is to demonstrate the QEMU support. And I'm not going to show just a simple hello world, which doesn't really do anything advanced. Rather, I'm going to show how you can utilize the Bluetooth hardware of your laptop to test Bluetooth functionality in Zephyr. So what you can do and what we support natively is you can export your Bluetooth adapters that are running in Linux to your QEMU-based Zephyr instance, and Zephyr can then use that as a standard Bluetooth controller, and you can experiment with whatever basically that Zephyr supports. So here in the background I have the HCI analyzer called BTMon from Lucy, and then in the window in front I'm going to run the Zephyr application with the simple make run command. Let's see if that works. There's a slight chance for demo effect here if something goes wrong, but no, that one actually worked. So on the left there, you can see the communication that Zephyr inside QEMU is doing with my laptop's Bluetooth controller, and on the right there, you see what the Zephyr console is printing. And now I'll just do a quick test here from my phone and try to scan for this application and connect to it, and you should see that a device connected. There there we go. All right, so that's now my phone connected to Zephyr running inside QEMU with the help of the Bluetooth adapter of my laptop. This is a simple heart rate sensor demonstration. So I can here from the application enable heart rate readings. I think it's that one. Then you'll see that it starts sending once a second and you're reading to the phone. So that's how simple it is to do Zephyr development, even if you don't have any hardware, if you want to get like an early start or prototype things. Another thing I wanted to show, just briefly here, is since the Zephyr boards have quite limited memory, it's good to be aware of exactly how much your application is using and where exactly the memory consumption is going to. And since most of the things are statically allocated, it's quite easy to do this analysis, and the build system actually provides some nice targets for that. So there's, for example, a make RAM report target, which will show you a breakdown of exactly where your runtime memory consumption usage is going to. That one is not looking so good. Okay, there you see it better. So, so you can see the total amount. So this is the QEMU target, which is not particularly optimized. So you can see down there 82 kilobytes, and you can see where exactly the memory is going to, how many % is going to different modules, and so on. And another target is ROM report, which will show you then how much flash would be used in a similar way. There you go, so that's 120 kilobytes. And this is available for any of the different target boards that you can build Zephyr to. All right. And a bit more about where you can find information. We have obviously a website, zephyrproject.org. Zephyr IoT is the Twitter handle, if you want to follow us. On the Freenode IRC network, we have our own IRC channel, which is quite active, and people will answer questions there if you have anything about Zephyr. We have a mailing list, and I mentioned earlier already that the code is available on GitHub. So that's actually what I had. Let's go to the questions.
Thank you very much for this nice overview and demo. And now it's about 10 minutes for questions.
Thanks for presentation. Can you say about the requirements for vSource? Can I write it on ARM Cortex M3 microcontroller with, for example, no MMU? Small
yes. Yeah, so we don't actually require an MMU. If you look at the boards that Zephyr supports, I think the most common one is Cortex M4. There are many boards with that, but we have even Cortex M0 support. If people are interested, by the way, I have some Zephyr boards with me. Some of them have as little as the Cortex M0 and 16 kilobytes of RAM and so on. So yes, you can do it. And actually, we have two QEMU targets. We have the x86 target, and we have also an ARM target. And the ARM target is actually the M3. So you can run it in QEMU as well.
Thank you. The next question.
How does Weld place outside the Cortex-M land? I mean, will it make sense to run it on, I don't know, MSP 430, which is 60-bit microcontroller, or something as big as Cortex-A, or not?
Cortex-A, possibly. There have been those questions. But well, in my opinion, if you can run Linux on a piece of hardware, you should run Linux on it. If you can't fit...
I mean, not always. I mean, for example, Linux could be a Linux overhead one with too much for the application.
Sure.
Would then the Zephyr make sense, or not? Or should I look elsewhere?
Possibly. It depends on the exact use case in question. But about the 16-bit that you mentioned, that's something that wouldn't work. Because right now, Zephyr requires at least a 32-bit platform. There are too many places in the code base which have hard-coded assumptions that you have a 32-bit architecture. Thank you. Yeah, no problem.
Thank you. There's the next question from here.
Thanks for the presentation. There was a question about Cortex M0 or Cortex M3 support. Yep. Do you have any numbers about minimal requirements of flash and RAM?
It depends very much on what application you want to run, how many features you want to enable, how simple can it be. The typical Bluetooth application, which I'm mostly familiar with, will consume anywhere from about 70 kilobytes of flash to some 120 kilobytes of flash, so that's roughly where you're moving. If you enable lots more networking features, it's possible it starts going closer to 150 kilobytes or so. RAM-wise, well, you can do very simple things with 8 kilobytes. 16 kilobytes gives you already the Bluetooth stack and most things that you can do with it. And then if you want to be very comfortable with what you're doing, then I would say from 32 kilobytes up. One thing to keep in mind with the flash is that if you want to go with this two-slot approach where you have the old and the new OS image, then you need the double amount basically from your flash for that.
Thanks.
Yep.
Thank you. There's the next question.
Okay, several very short questions. What about USB support?
We have USB device support. So there are several boards which support USB device, and we actually have sample applications. We have one actually for the Bluetooth stack, so you can make a Bluetooth dongle, USB dongle out of Zephyr, plug it into your
So
PC.
post host and
That host, USB host we don't yet have. There's been some interest expressed in that, and most likely it will show up, I'd say, within a year or so, but at the moment it's only USB device support that we have in Zephyr.
Okay, the second question, like microblaze softcore architectures, like FPGA-based softcore processors, is there support for this?
Well, the FPGA ones, there's the Nios 2 from Altera. So Altera has some FPGA-based platform. That's the only thing I know of, and it's actually an area I'm not really specialized in that much. But I know that we have at least those which are FPGA-based.
Mm-hmm. And a little bit more small philosophical small question about is safety critical or security critical support? Is it on high in priority?
I would say it's perhaps the highest, or at least one of the highest priorities at the moment. It's something we're very much looking into. We're running various static analyzers in preparation for this on the code base to see how much is there that we need to fix, and we're kind of trying to preemptively fix these things so that we don't have a huge workload once we try to do it officially, formally, this kind of security certification.
Okay, thank you very much.
Yep, no problem.
Yeah, so I have a quick question about the device tree support.
Yeah.
You mentioned you're using device tree to describe hardware, but
yes.
How do you fit it into all these small devices? Do you somehow compile it into
it's compiled in advance. It's basically used to configure the build. It doesn't actually, there's not that much runtime stuff that happens. So we use the same language to describe the targets, but it's not a runtime-based thing as such.
So how do you handle multiple nodes in the device tree if you have like multiple SPI controllers? Do you somehow tweak the device tree?
You're asking about an area which I don't know that much about. I mean, we could go digging into the source tree and I could find it to you, the DTS files that we have there.
I'll get you later about that.
Okay,
thanks.
Sure. Yeah, no problem.
Thank you. The next question.
You said about Zephyr Realtime OS, and it was a presentation just before you about real-time kernel. Any connections, any comments?
I missed the previous presentation, unfortunately, so I cannot comment on that
okay,
one. Probably not.
You probably know about real-time real-time support on Linux kernel.
Yes.
Do you use it? Does Zephyr use it?
Well, Zephyr is a completely separate project, so in that sense, no, it doesn't really use anything.
And so what kind of real-time can you provide over more or less standard Linux kernel? Is it possible, I wonder?
It's an area that I'm not really an expert in, but the Zephyr scheduling model is very simple. So you can, I mean, I would say there are less kind of moving pieces in the puzzle when it comes to Zephyr, that it's fairly easy to make something that has deterministic scheduling properties with it, at least.
Okay, thank you. One follow-up question.
I would like to just follow-up comment on the real-time stuff. For example, the Bluetooth controller support that we have in Zephyr, that's extremely time-sensitive of getting the packets over there and processing them exactly at the right time. So that one is taking advantage of the fact that we can do this kind of lot of stuff.
So I have a follow-up question.
Yeah.
Can you replace the scheduler in Zephyr with something which is like really hard real-time? Is that possible?
Possibly. It's software. I mean,
Yeah, but is there some sort of
I haven't
API?
looked at the API and the way it integrates with everything, but I would imagine it's possible. But
Okay. Cool, thanks.
yeah, no problem.
Thank you. There's the next question.
Thanks for your talk.
Yeah, no problem.
You have an ability to build the system from scratch because it is quite a new project. And could you share some ideas? How do you handle errors? I mean, if there is an error in application or in the microkernel, what do you do and how do you decide?
Well, it depends what kind of error it is, but we have recently taken into use this kind of memory protection features that are found on some architectures. So you will actually get proper faults when, I don't know, somebody accesses a null pointer or something like that. But generally, I mean, when the application does something bad like that, you will get a stack dump where you can then translate the memory address that it shows to some place in the code, or then you can connect GDB or some other debugger to what they're using to QEMU or to one of the boards that we support, and you can then do analysis of what's happening there. So I think quite similar tools that are available for other OSs like Linux as well.
And do you have some special restrictions on being self-healing? I mean, Zephyr should be very reliable and maybe recover from some errors or have some special policy when to handle, when to shut down.
It depends on the subsystems. So we do classify things into something that's a critical fault that requires restarting and something that's a runtime error that can be handled. I think that might be a little bit differently handled depending on what subsystem you look at in Zephyr. The Bluetooth controller stack is heavily riddled with asserts here and there to figure out like what absolutely shouldn't happen, and those then can be mapped to an overridable handler from the application that can, for example, restart the device in question or something like that.
And how much time does it take it to start? I don't
know. That depends on the board, I guess. But most Zephyr boards are instantaneous almost. Sorry?
Just to have some insight. So microseconds.
It depends on the board. So it's faster than you can kind of measure without some special tools, I guess.
Thank you.
Yeah.
Thank you. I think we have time for the last question.
Okay.
How do you compare the Zephyr OS to RTOS?
I'm not super familiar with Riot, but I would say that the general kind of differentiating factor with Zephyr is that we have lots of extra higher level features and services on top of the core kernel, like the networking stacks, the Bluetooth stack, high level protocols. It's kind of a bigger ecosystem than there. So if you want to make a product with Zephyr, you often with other RTOSs, you have to go and source the other modules from elsewhere, possibly pay for them. With Zephyr, we try to have as much as possible as part of the project, so you get everything there in the same package.
Okay, so thank you. The time is over. One question to you. What is the best question you receive today?
They were all very good questions. I don't know, I wouldn't be able to say. Who will do the selecting if I don't do that?
Okay, it's basically you, probably Dmitry. Do you have any opinion?
And they're all very good questions.
No, actually I don't. So we force you to pick someone.
Yeah.
The guy receives a T-shirt.
This question about the Riot OS and so on, because that's something I should have probably brought out in the presentation as well. What's kind of the key competitive advantage with Zephyr compared to many other RTOSs? So that was good that was brought up.
Okay.
Who asked you, good? And who asked this question?
The guy on the phone there.
Okay.